Thank you. So essentially, in this short presentation, I'll try to summarize some of the recent developments that have happened in this field of Hopfield networks over the past few years. And as Jose said, I'm sure many people in this room are extremely well familiar with the old classical Hopfield networks from the 80s. They used to be very popular among statistical physicists, computer scientists, computational neuroscience people, etc. But it turns out that there has always been a problem associated with them. And roughly speaking, the problem with the old Hopfield networks is that there is only a very small amount of information that you can write down in those networks. And as I will show you at the next slide, it turns out that this limit is so annoying that you can't really apply the old Hopfield networks for interest in modern machine learning problems. And when you see this combination of words, modern Hopfield networks, sometimes they're also called dense associative memories, it refers to sets of ideas that have been recently developed that makes it possible to significantly overcome that limit. So essentially, in the modern Hopfield networks, you can store as much information as you would like. And I'm going to try to explain all this in my short presentation. So first, let me start with a fairly general question. What is a Hopfield network of associative memory in the most general sense? So it's a recurrent neural network, and it is described by a state vector that evolves in time. So pretty much, similar thing how LSTM operates. But the unusual aspect about Hopfield nets is that in addition to all the familiar properties of RNNs, Hopfield nets have something that is called an energy function. And the idea is whatever the recurrent dynamics of the neural network is doing, the energy function always decreases. So you can think about it like this. You can start from some state that is high up in the energy, and then the state relaxes towards one of the local minima. And whenever the network reaches that local minimum, we say that the network recovered the memorized state. So a couple of commonly used use cases for this idea is pattern completion and denoising. So in the pattern completion case, you can give to the network a state, the initial state that hints to the network which of the local minimum it should go into. And then we can run the temporal dynamics, and you can see that associative memory recalls the nice image of the bird. In the denoising case, you start from a noisy image, and you ask the network to remove that noise. So pretty much like we do in diffusion models. And again, we see that the network solves this problem pretty well. And if I take this simulation and I stop it somewhere in the middle, you can see that, I don't know if you can see that, but there is a little bit of in the background, you can see the same bird, hopefully. Or maybe you can't, because the screen is like too dim. But anyway, so if you saw it, then it actually illustrates a nice property of this network, which is it's actually a very collective system. So it involves activities of all the neurons and all the memories, and they all play in concert to solve this task. So that's the general idea of this kind of computation. So this idea was famously formalized by John Hopfield in the 80s. And what he proposed is the following simple system. So you can think about this neural network as a lone vector sigma I of binary spins. So it's an n-dimensional vector. And each sigma I is plus or minus 1. So it's like an Ising-like variable. And the idea is that you can describe the energy function, which is this simple quadratic form of those Ising spins. And this system has been studied in a number of papers. And what people realized is that it works as a very nice system of associative memory, but only if the number of neurons n is big and the number of memories k is small. So specifically, the best that you can do in this simple system is to store the number of memories that grows linearly with the size of the network. And that's a classical result. For example, Chaim Sampolinsky wrote several foundational papers on this model. Now, if you think about this, it's a little bit annoying because it really tells you that you can't really store a sufficiently large number of memories for interest in machine learning applications. Think about, for example, of dealing with simple binary images. Let's imagine that I give you a grid 32 by 32 pixels. So roughly speaking, you have 1,000 neurons. And essentially what this bound tells you that there is no way that you would be able to store more than, say, 130 memories. And clearly, if you think about all possible binary images that you can put in a 32 by 32 grid, there is way more images that you would like to, to work with. Think about, for example, of Japanese kanji characters, right? An educated Japanese person needs to know 5 to 10,000 K of those characters to read a newspaper. And like the simple Hopfield network simply cannot meaningfully work with that amount of information. So this raises a question, can we do something about it? Can we somehow change this energy function and dynamics so that we can actually store way more information in this network? And this is what modern Hopfield networks or dense associative memories are. The idea is that you need to go from quadratic Hamiltonians to more nonlinear Hamiltonians. So you need to order higher order interaction terms in sigmas. And it turns out that if you do it in the right way, you can achieve either a power scaling relationship for the number of memories when the power is bigger than 1, or you can even achieve an exponential storage capacity. And essentially, the reason why we have called this model a dense associative memory is because the total amount of configuration space is 2 to the power n in both classical and dense case. But in the classical case, you only fit a small number of memories into that configuration space. But in the dense memory case, you can pack those memories in a much denser way so that you can actually fit an exponentially large number of memories. So that's a general idea. And this model faced some criticism, which originates from the following argument. So it is very tempting to think about the coefficients in front of these coupling terms like Tij, and if you, for example, put in a cubic term, there will be a tensor with 3 indices. It is very tempting to think about these coefficients as synaptic strength between the neurons. And what we have recently realized that this is a completely wrong way to think about the system. Because if you think about it that way, then you immediately need to conclude that these systems are highly unbiological, right? Because in biology, most neurons, they tend to interact in a pairwise way. And here, it seems like you would require to have some kind of many-body interactions. Now, it turns out that that's a wrong point of view. And the right point of view on these systems is the following. You need to think about them as effective theories. So essentially, you can introduce a large number of hidden neurons into the network so that interactions between all the hiddens and all the visible and all the neurons in general are only pairwise. And only after you integrate out those hidden neurons, you end up having these higher order nonlinear terms. So in that sense, dense associative memories or modern Hopfield networks, they are pretty much in the same universality class as the classical Hopfield networks from the perspective of biological plausibility. So they only have pairwise synaptic interactions. And another, and I guess, yeah, I'll mention this later. So yeah, if you want to read more about this, you can check out this paper that is mentioned at the bottom.
How many hidden?
Say it again?
How many hidden neurons do you need?
You can, well, you can have as many as you want.
But how few?
Say it again?
But how few can you have?
How few? You can have as few as you want, yeah.
No, but the number of hidden units is the number of memories.
Yes, the number of hidden, correct, yes, okay, I understand the question, yes. The number of hidden units scales linearly with the size, with the number of memories, that is correct. But the
it's not dense anymore.
in some sense it is dense. First of all, if you integrate them out, right, then you have a network with n neurons and exponential storage capacity. It is non-biological, but it's a fair statement, right? You have n neurons, you have 2 to the power n over 2 memories. Second, it turns out that there is a ton of interest in machine learning problems where you would actually like to keep the number of feature neurons fixed, but the number of hidden neurons can be pretty big. And essentially, this is the interest in the regime where these networks end up being quite helpful. I'll show you some examples later. Right, so the next thing that I want to say is the following. Recently, people have realized that if you take this idea of dense associative memories and you take a limit in this class of theories, you specifically pick some activation function to be a softmax. You can show that these models reduce to the attention mechanism that is commonly used in pretty much any modern neural network architecture. So for example, Ethan told us about large language models yesterday. These are transformers, and attention is the core computational block of those models. So the cool thing about this is that there is not so much theory about what transformers are doing, but at the same time, there is a fair amount of theory about Hopfield nets. And if you have this mathematical correspondence between these two kinds of models, you can actually try to interpret some of the computational properties that transformers are doing through the perspective of associative memory, through the perspective of attractor dynamics, Bayesians of attractions, etc., etc. And also you can try to think, can you actually improve transformers? Can you actually make them better? Like by using, again, utilizing this theoretical method. So another thing that I want to briefly mention is that technically there is absolutely nothing that stops us from having very deep dense associative memories with many hidden layers. And we can also easily introduce interesting inductive biases like convolutions, pooling, etc. And I should also say that Chingiz has done some very cool work on incorporating convolutional structure in networks with feedback. There are many interesting machine learning applications that people have tried to implement using these new ideas. I don't really have too much time to go into any details about each of these papers, but I want to show you this highly subjective list of papers that I think are very interesting. So for example, in this paper, people have used dense associative memories for solving a highly non-trivial for conventional feed-forward deep neural network problem of immune repertoire classification. And I don't see Mickey here, but it's actually the kind of problem that he extensively discussed in his talk yesterday. So when you have a lot of sequences, the amount of information in the labels is very small, and the signal is very sort of diluted among all the sequences. It turns out that you can very meaningfully use a high memory storage capacity regime of dense associative memory for solving these kinds of problems. Another interesting paper is listed here. What people realized here is that the hidden neurons, those auxiliary neurons that need to be introduced into the network for making it biological, in a sense, of pairwise interactions, actually, in a quite meaningful way, correspond to place cells in the hippocampus. So you can run like some meaningful simulations, and you can see that they develop place cells, and the whole architecture makes some sense given the anatomical structure of the cortical hippocampal loop. So I don't think I have too much time. So if I had to summarize the several new developments that have happened in the past few years in this little field, what I would say is this. First of all, the annoying limitations for the memory storage capacity that we're all aware of, by and large, are gone. So in these new networks, you can write as many memories as you want. Dense associative memories can be both continuous and binary. There's absolutely nothing special about a binary case. You can make them continuous, you can backpropagate through them, you can do all the nice tricks that we like to do in machine learning. They do not require many body synaptic weights. So it's, they can be perfectly formulated in a very nice pairwise fashion. Another thing that I didn't have time to discuss, it turns out that there is a so-called Lagrangian formulation of these networks that is very natural, and essentially, if you think about these networks in terms of their Lagrangians, in a quite similar way how we use Lagrangians in the classical mechanics, you can construct crazily complicated networks with global Lyapunov functions and highly nonlinear dynamics, and everything is like very controllable. So it's a very nice framework to use for describing these models. And lastly, they can be very deep and they can have structural connectivity. Thanks.
Thank you very much. That was very nice. So a few things before people can start to ask questions to Dima. On the meantime, all the other speakers can move to the front, and Grant can give a 2 slides presentation about his work, so he can move to the front. So you have 3 things going together.
Question?
Herbie.
So just that maybe you should just comment on, I mean, the structure of the attractor space is one thing, but as you showed so nicely for the original Hopfield network, there's very large convergence, or regions of attraction, which allows you to solve noise problems, etc. What is the story about the dynamics of these many, many more dense attractors?
Yeah, great question. And in fact, this question has been studied in detail in this very nice paper by Dmitry and co-authors. So essentially, to make a long story short, the Bayesians of attraction are as big as in the original Hopfield network. You might find it a little counterintuitive. You can ask, I have 2 to the power n neurons, and I want to put an exponential number of attractors. How is it possible that they have the same
That's
size?
sort of the basis of my question.
Right? But in fact, there is a very simple and intuitive answer. The largest memory storage capacity in this class of models have the memory storage capacity which scales like 2 to the power n divided by 2. So it's a square root.
It's still very sparse.
It's still extremely sparse, right? So if you have 2 to the power n, which is a huge number, the square root of that number is way smaller. But the cool thing is that the square root of that number is like way bigger than linear in n, right?
So your proposal is that it solves both problems.
Okay.
It solves both problems, exactly. And like these folks, they actually quantified the sizes of the basin of attraction, and they rigorously prove that they are capital O of n. So it's
Okay.
same as in classical Hopfield.
So you have one more question, but remove your computer so I can have Grant to put his computer while you answer the question.
Yep.
Go ahead.
Great. Thanks for the really clear talk, Dima. My question was about the Lagrangian formulation. So time in this case is kind of the different steps of the network, but how do I interpret, like, okay, I have Q and Q dot, like, what is there kind of a further interpretation of what that is?
Right. So first of all, there's no.
Here.
So first of all, there is no Q and there is no Q dot, and like the name Lagrangian, frankly, is somewhat stretched in this formulation in the following sense, that the whole system does not actually have the structure of the Lagrangian mechanics. So the dynamical equations are not Euler-Lagrange equations. But the reason why it's a meaningful name is the following, that if you write the global energy function, the energy function is given as a Legendre transform from the Lagrangian. And that's why we picked, this name for this auxiliary function. But essentially, the Lagrangian function, it's a property of the activation functions. You can literally stack multiple dense Hopfield layers on top of each other. Every layer will have its own activation function or its own Lagrangian. And the cool thing is that you can formulate the convergence properties entirely in terms of the Lagrangian functions. And this is a much more general thing that you would normally be able to do. For example, there are this classical old paper 1984 by Hopfield where he constructed the energy function by inverting the activation function. It turns out that it's a very problematic construction for modern systems because in modern systems you like to use softmaxes because we want to do attention, we want to do transformers, etc. And you cannot invert a softmax. But this new formulation actually allows very natural construction of these, collective activation functions, divisive normalization, pretty much anything that you want.
I'll ask you more offline.
All right. Thank you. I think.